Hello everyone, my name is Awais Akhtar and I'm here to present my BTech project on recursive least squares. Let's have a look at the index of my BTech project. First, we shall discuss the introduction to my project. Then we will look at the related works on recursive least squares. Then we shall discuss the recursive least squares algorithm and see how it is being applied on time varying data. Then we will have a look at the Kalman filters, recursive just-in-time model, recursive locally weighted least squares, results, conclusions, and references. Recursive least squares is a well-known adaptive filtering algorithm that efficiently updates the recorded historical data based on the new data and the past data discounted by a forgetting factor. An important step for building a successful soft sensor is using recorded historical data to sustain the performance. In this project, we will discuss the just-in-time learning model to solve the nonlinearity modeling problem. We will discuss an adaptive algorithm which prioritizes the most recent samples as well as nearby samples to solve both time-varying and nonlinearity problems. Let's have a look at the online adaptation of soft sensors. In this, we are using historical input data X and lab measured output data Y in our modeling technique. The lab measured output data is also used in the updating strategy along with the online input data, which helps the soft sensor to make predictions. The newly generated predictions are again used in the updating strategy to model for better modeling of the parameters and to generate new predictions for the newer data. Moving on, let's have a look at the related works. The existing adaptation methods have been categorized into three approaches: instance selection, instance weighing, and ensemble methods. Instance selection is also known as the moving window technique, whereas instance weighing is also known as the recursive adaptation technique. Wang et al. Proposed an optimized version of moving window of PCA called the Fast Moving Window Principal Component Analysis (FMW-PCA). Adaptation of nonlinear models has also been reported in the literature. Liu et al. Proposed a moving window kernel PCA. Li et al. Proposed a recursive nonlinear partial least squares algorithm to solve both nonlinearity and time varying issues encountered in process modeling. Recently, just-in-time modeling approach has been proposed to address the nonlinearity problem in soft sensor development. Just-in-time approach is a local learning method. The time varying issue cannot be solved unless adaptive mechanism is introduced into the just-in-time framework. Let's have a look at the recursive least squares algorithm. Recursive least squares algorithm can be considered as the recursive equivalent of standard least squares algorithm. In RLS, a single new data point is analyzed in each algorithm to improve the estimation of the model parameters. We use the Sherman-Morrison-Woodbury formula to avoid computing matrix inversion at each iteration step. We also define a forgetting factor lambda in order to define how much weight to give to the past input data. It is important to note that the aim is not to minimize the overall mean squared error like for least mean squared. Hence, RLS tends to much faster convergence but has higher computation cost. Let's have a look at the implementation of recursive least squares. It is important to note that the aim is not to minimize the overall mean square error. We are using the following formula: AX is equal to B, which can also be written as A transpose A times X is equal to A transpose B. Now we are adding the new data as a row in our matrix, which helps us convert X into X new, and we get this following formula. uh, we have to calculate the inverse of this part to solve the following equation. Hence, we use the Sherman-Woodbury equation to calculate the value of this matrix, inverse matrix. And this way, we avoid computing the matrix inversion in each step. The Sherman-Woodbury Morrison equation helps us perturb the, uh, the matrix from rank n to rank k. Let's have a look at how recursive least squares algorithm is applied on time varying data. In the following two plots, the left plot uh, has the forgetting factor of 0.9 on time varying data, and these are the parameters of the model. Uh, the right graph has a forgetting factor is equal to 0.5. Moving on, let's have a look at Kalman filters. The Kalman filter algorithm is used to assist in tracking and estimation of the state of a system, but there is always some level of uncertainty. With Kalman filters, we can mitigate the uncertainty by combining the information we have with a distribution that we feel more confident in. Only estimated state from the previous time step and the current measurement is required to make a prediction for the current state. Kalman filter is used to determine how much of the new measurements to use to update the new estimate. The lower the weights, the lower the model trusts the observations compared to the predictions. Let's have a quick look at the implementation of Kalman filters. This, uh, this is the state prediction of Kalman filter. Over here, Q is the process noise covariance, R is measurement noise covariance, A relates the state to the previous step, B relates optional control input to X, H measurement equation relates to the state of the measurement YK. These are the equations which are used for a prediction, update, and observer respectively. Moving on, let's have a look at when Kalman filter is applied to the following measurements. The graph in the blue line shows the actual measurements, whereas the orange line shows the Kalman filter predictions. Moving on, let's have a look at recursive least squares versus Kalman filters. The process of Kalman filter is very similar to recursive least squares. While recursive least squares update estimate of a static parameter, Kalman filter can update and estimate an evolving state. These are the equations used in Kalman filter and recursive least squares algorithm respectively. Recursive just-in-time model. The goal of recursive least squares algorithm is to accommodate the latest data point to estimate the model coefficients beta t. In this model, we are using a forgetting factor which gradually discounts the old data. The key point in this recursive least squares is the update of covariance matrix. The success of traditionally locally weighted least squares depend on two main loading vectors, pk and qk. For recursive partial least squares, the most important step is to assign appropriate weights to the covariance matrix by putting a forgetting factor to the lambda on the past data. So in this model, we are assigning higher powers of lambda to the previous matrix and lower powers of lambda to the newer data. And by doing so, we are assigning more weightage to the newer data compared to the previous data. Let's have a look when recursive just-in-time model is applied on demand forecasting data. In this, the left graph shows the um, uh, the predictions on the actual data points with a forgetting a factor of 0.5, whereas the graph on the right hand side shows the predictions on the model with a forgetting factor of 0.99. Recursive locally weighted least squares. In the proposed algorithm, a moving window approach is adopted to update the database. The two weighing matrices Wt and Ws are formulated to account for time varying and nonlinearity issues respectively. The most recent sample is added to the database while the oldest one is removed. Means enter the database. Set up the size k as the number of most recently samples to be prioritized. Assign time weights to each historical sample by forgetting factor lambda. So by using this formula, we are assigning a moving window, and we are assigning the powers of lambda to the newer data points in the moving window. Assign space weights to each historical sample by using Euclidean distance. This is the formula of the Euclidean distance, and for the weight matrix, for the space weight matrix, we are also using a balance factor which has a value between 0 and 1. The final weighing matrix looks as follows. Perform locally weighted least squares algorithm using W. The balance parameter rho is between 0 and 1 is introduced in order to determine the strength of adaptation to the most recent samples. The proposed algorithm is not completely a recursive regression, indicating that the similarity in space may also be relevant to the current samples and will play a key role in predictions. Let's have a look at when recursive locally weighted least squares algorithm is applied on the demand forecasting data. The recursive least squares just-in-time model has a lambda value equal to 0.5, a k value equal to 3, and rho value is equal to 0.6 on the left plot, whereas it has a value of 0.99 for the forgetting factor lambda, 3 for k, and 0.6 for rho on the right plot. Results. Moving window least squares achieved more improvements than locally weighted least squares, which indicates that the time varying issue is more evident than non-linearity issue in the database. Locally weighted least squares is not able to track the process dynamics during certain periods, which is due to the limited process information contained in the database. If the just-in-time approach adopts a fixed database, the future process information will be missed, and thus the model performance will deteriorate in real applications as time progresses. Recursive locally weighted least squares gets a better prediction performance since it takes advantage of both adaptive and locally weighted algorithms. Conclusion. Traditionally, recursive algorithms and locally weighted algorithms prioritize relevant samples by assigning higher weights to more relevant samples in terms of time and distance independently. In order to deal with time varying and non-linearity issues simultaneously, the recursive locally weighted least square algorithm is proposed. Recursive locally weighted least squares is formulated by merging recursive and locally weighted algorithms into the unified just-in-time framework. Let's have a look at the references used in, in the algorithm. Thank you.